Yeah. Yeah, and I noticed another person who turned it in said it was a gas, and I just wanted to make sure we're all on the same page.
Yeah.
Okay, so the way you find temperature of interest, which was, here or so, then you find the pressure of interest, and then you see where it intersects. Okay, so anyway.
See, I guess it's good you explained it because I thought it was like solid. That was good.
Yeah, I don't know.
No, it was a solid explanation. Yeah, that's good.
Oh boy. So, on to today's lecture, which hopefully is this one. Yeah, because we did solution concentration. I really, we're only going to get through part of it, but then we're going to skip to the assignment slide because that's just how it works. We won't get through this whole section. So one of the things, the title is effect of solubility, effect of temperature on solubility. And so just remember, when we talk about solutions, we basically have a large amount of solvent, and I forgot my stylus, so this is going to be uglier than usual, and we dissolve a solute in there. Oops, goodness. Now, usually, a lot of times the solute that we dissolve is a solid, okay, and usually the solvent is a liquid, a lot of times, okay, but not necessarily. And I was getting ready for today's lecture, and I'm kind of like, if you want to increase, if you have sugar and you want more sugar to go into your water, do you add heat or do you cool it down? You add heat, exactly. And that's kind of, we think that's the same case with salt, as far as I know, sodium chloride. Most things, or a lot of things, what we think of is if we want to increase the solubility of our solution, we heat it up, and you can put more, okay, but that's not always the case. And that's where we're actually going to look chemically behind the scenes why that's not always the case. There are some cases where if you jack up the temperature, the solubility goes down, depending upon the thing you're dissolving. And your solute doesn't have to be a solid, it could be a gas. Like carbonated beverages, it's CO2 is the solute. Water, sugar water basically is the solvent. And the solvent doesn't have to be a liquid. That's weird.
Which is so interesting.
Yeah, it is. Because like when we talked about a carrier gas picking up, to me, you were making a mixture of, carrier gas was helium and it picked up, carbon tetrachloride or something, okay? So kind of be thinking along those lines. But we're definitely going to start out with your typical dissolving a solute in a liquid solvent. So these, I think, will work. Each temperature has its own saturation amount. So, yeah. So we kind of talk about sugar, if you trying to dissolve a lot of sugar into water, well, if you heat it up, then more is going to go in. So, yep. Yes. So the term ordinal means basically kind of like, oh, there's no number associated with it. So we do have this kind of general terminology in order of decreasing solubility. So if something is soluble, and actually I brought along the CRC handbook to kind of show you this. If something's less soluble than soluble, they call it moderately soluble. Then less than that is only slightly soluble. And then insoluble. I think that's it. So it's ordinal. There's no number associated with it. Now, I haven't shown you guys CRCs. This actually is a kind of an older CRC, 1988. But really, did these things change? I kind of tease that this is just a bunch of chemical constants that who could really do all this, okay? A lot of this stuff you can get on the internet. The CRCs, if you ever have to use one, are kind of broken up. What I use, they have an inorganic section, inorganic, and then they have an organic section. So actually I'm going to go to the inorganic section. It says physical constants of inorganic compounds. And then like if you just look at that last column, okay, this is the solubility of these compounds. And notice sometimes it gives a different solvent, like nitric acid, sulfuric acid. If it doesn't, it's just talking about like, it doesn't, it's just talking about soluble in water. Sometimes it gives a number, sometimes it gives a number. So these are two different assessment organic compounds. So this last column over here is all solubility. Oh, wait, yeah. See, I didn't see this when I showed you. So it says cold water, hot water, other solvents. So this is the substance, yeah, this is the substance, and this is the solubility. Yeah. And they have like little footnotes sometimes. So, yeah.
When it says other solvents, is that the other solvents like present, or is it?
That's the, like if you were to go ahead and start fresh with this solid, what other solvents
Oh,
has the solubility been investigated to be in?
Oh.
Yeah. Yeah, I think so. Cool. And I guess it's not necessarily ordinal. I mean, under cold and hot water, they give you sometimes some numbers. Actually, we're gonna look at a table here that gives, or not a table, but a graph here with some numbers. Yeah, I like it. So solubility, we can kind of talk about three kind of degrees of solutions. Okay, if you're dissolving a solute, maybe a solid solute, like we saw in a liquid solvent, it's saturated. I say if you see sludge at the bottom, okay, sludge at the bottom, the thing is saturated, right? Unsaturated means, and to me, unsaturated, you can test it just like by trying to put more solid in, and if you stir it and it goes away, then it was unsaturated. Okay? So, supersaturated, we have, in physical science, we have these kind of super conditions. Actually, we have superheated, we have supersaturated comes to mind. I'm sure there are other supers. The word super just means that it's above and beyond. So it's possible, and I didn't bring an example, it's possible to have a solution that has more solute in it than it really should, according to the literature. It's beyond its solubility. Anything super is really kind of tenuous, and anything super is just itching to go back to normalcy. Okay, so supersaturated. And it's not too hard to supersaturate a solution depending upon the solute and the solvent. But it, like I said, it's not very stable.
So would the solute start to degrade or would something?
When they start to crystallize again?
It's not very stable. The example we're going to see of a supersaturated solution is sodium acetate. There's lots right there. So sodium acetate, I don't know, just to the nature of the ionic compound and water, you can put more than it should be. And I don't know if this is your question. It doesn't degrade. It totally doesn't degrade. The itching part is, in this case, to come out of solution, to form a sludge. That's the itching part. Okay? So it's not going to do anything other than to get out of its super situation, which in this case is saturation. That's a lot of S's. Okay. So we're going to look at some movies, unsaturated. Yay. Here's the deal. This is the sludge at the bottom. Okay, now kind of from left to right, think of kind of time going on. So when you first add your solid solute, it basically it starts a dissolving process. Okay. Then here, notice that, and the length of the arrow is important. So you guys would probably tell me that the dissolving is more than the precipitating. That black arrow is precipitating. Okay? So we have a net dissolving, right? Given enough time, when it reaches basically what we call saturation or equilibrium, as long as you have more than enough to go ahead and saturate your solution, this is what the sludge looks like after time. And the difference between the middle one and the end one, of course, is the length of these two arrows. Okay? Notice that we have precipitation, and we have, that's the black one, and then we have dissolving, that's the pink one. So what I think is so cool about this is that we use the word dynamic a lot. Dynamic just means it's like never stopping. And actually, this is what we call an example of a dynamic equilibrium. So that's to say that what's a solid now may not always be a solid. Okay, it's going to go from solid to, we'll call this AQ. okay, assuming that it's water is the solvent. It's going to actually go back and forth. But do you buy this? If these arrows are equal, if the rate of precipitating is equal to the rate of dissolving, then this solution concentration is constant. Okay, so that's important. So we have this kind of dynamic equilibrium going on. And we're going to go back to those arrows, the pink arrow and the black arrow coming up. So, yep, this is what I just described, my little hand warmers. So here's where we get to kind of the title of this part 9 is. Basically, we generally think if you want more solid to go into solution, you heat it up. Not always the case. But it's the case with a lot of things. So I want to kind of write the dissolving process in terms of like a chemical reaction. And with chemical reactions, we read them from left to right. So dissolving, I'm going to write from left to right. We are starting with the individual solid solute and the solvent, right? They're by themselves. And we could say the product that we're going to get is, dun, 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 the solution. Kind of from left to right, kind of how the process is going. Well, that's the process in dissolving. But like we saw a minute ago, it's a dynamic process, and even though you're dissolving, at some point, especially at saturation, you're also dissolving and you're precipitating. You're dissolving and you're precipitating. So at that point, then actually, we're going to represent that with a two-way arrow. And I can't remember if Chem 1 we talked about this. This top arrow is the dissolving process. This bottom arrow is the precipitation process. Does that make sense? This is PPT for precipitation. This is dissolving. So this actually is representing that third beaker. I know it because we're showing actually the length of these arrows are an indication of how much you're going to dissolving, how much you're going to precipitating. If you see equal lengths of your arrows, okay, the rate at which you're going from a solid to a solvent dissolving is equal to the rate at which your saturated solution is breaking down back into its components, precipitating out. Okay. So that's the third beaker. All right. So what happens if you go ahead and jack around the temperature, mess with the temperature? Now, we're going to not do all of Part 9. At the end of Part 9, it talks about what we call the Chatelier's principle of stressing a system. And we stress systems that are on equilibrium, going back and forth between, in this case, the individual solute and solvent and the solution that's mixed together. One way to stress it is temperature. One way to stress it is temperature. Okay? So when we think of increasing the temperature, we're going to be adding heat. And if we cool it down, we're actually going to be removing heat. And we'll talk more about that again on Monday. So here is a table that you're going to need to use for all 3 homework problems that you're going to do for Monday. But let's just kind of orient yourself to the table. Notice the units of concentration. So basically along the y-axis, we have how soluble is it. Each color is a different salt. We have potassium perchlorate, potassium sulfate, potassium nitrate, ammonium chloride, sodium chloride, and lithium sulfate. So each color is a different salt. And then along the x-axis we have temperature. Okay. Now over there, picking on potassium perchlorate, at 50 degrees Celsius, notice we've got 1, S, and 2. The 2 actually represents, if you are here anywhere in this region under S, okay, basically you are at an unsaturated solution of potassium perchlorate. If you are right at S, you're right at saturation. If you added more, you'd get sludge. If you didn't have quite as much, you could add more. And then here, if you are successful in getting any of these amounts, okay, above S, okay, to go ahead and dissolve, then you have a solution that is supersaturated. That's kind of how that works.
So the line always indicates like it's saturated,
Yep.
anything below is unsaturated.
Exactly, right at the saturation point. So I'm going to go ahead and circle one of these. One of these lines is not like the others. So I'm picking on lithium sulfate, and lithium sulfate's not the only one. Sesame Street, right? So according to this graph, for instance, at 20 degrees, okay, and again, the units over here along the y-axis are kind of different than we're probably used to. At 20 degrees, it's like maybe 34, I don't know, 34 grams of lithium sulfate per, no, I was looking at the wrong line, sorry. I was looking at the dark blue one. I want to look at this one. So at 20, maybe I was.
Yeah, right.
Not bad, okay. 34, not bad. Okay, good. So 34 grams of lithium sulfate per 100 grams of H2O. Now that's weird because it's not really molality, it's not molarity, it just is what we do solubility in. And I think that CRC kind of goes with that sometimes too. Okay. So, but if we look at its solubility at 60 degrees, which is warmer, and like I said, this is a little counterintuitive, you think that there might be more dissolved, but actually it is saturated at a lower amount, at about 30, maybe 32. Maybe 31. It's hard to read. Kind of got my thing mixed up. But my point is the solubility goes down with increasing temperature. Okay, and we're actually going to look at, if you know a little bit about the chemistry of dissolving for these ionic compounds, then you can anticipate which direction it's going to go with increasing temperature. And we'll get to that on Monday. All right, so just a little bit about solubility again. So, for instance, ammonium chloride, I brought ammonium chloride. I brought two salts to add water to. I forgot. No, I'll do that in a minute. Okay, so ammonium chloride, if you heat it up, it'll be more soluble. If you cool it down, it's less soluble. So if you look over, it's got the normal sort of increased solubility with temperature. You cool it down, it's less soluble. And that's actually what you're seeing. You're seeing the ammonium chloride precipitate out. Okay, so I said you can kind of understand, kind of behind the scenes, what is going on. We're going to watch this video, but remember Hess's law says, basically, if you have an overall process and you know the energy is associated with kind of each step, you can add them together and know the energy associated with the whole thing. Now, the cool thing is, no pun intended, is that if it doesn't happen in these discrete steps, that's okay. But if these are the things that need to be accomplished in order for the whole thing to happen, then you're set. Okay, so here is the video. Okay, so plus means it's endothermic. So it's actually kind of nice because it's consistent with all the stuff we talked about. This idea of breaking these bonds was endothermic. To break bonds takes energy. When new bonds are formed, and actually this right here, the hydration of your cation, your anion, when new bonds are formed, bonds of hydration, energy is released. So it just kind of depends whether it be endothermic or exothermic, depending upon kind of which one's bigger, the magnitude of which one's bigger. So this is where I say, don't blame me. I finally fixed this slide. This is the same substance. And the same substance a minute ago, we came up with endothermic by 2 kilojoules per mole, right? And I looked up on the internet, and that is totally right for KF. This slide, however, shows it exothermic. Do you guys have this one? Yeah. So it is very hard to read. This number right there, where it says negative 16 kilojoules per mole, actually that should be positive too. And it comes back to what is the when the waters surround those cations, what's the enthalpy of hydration? And instead of the energy being released, 837 kilojoules per mole, it's only 819 kilojoules per mole. You're like, really? So I think I got that, where I'm cool with it. So yeah, this is why I brought, in Chem 1, you guys took Chem 1, in Introduction to General Chemistry, one of the things we do at the very first is kind of do some kind of physical properties and thinking about the scientific method of discovery. But this is potassium chloride, this is calcium chloride, and this is ammonium chloride. Okay, so one is an endothermic process, and the other is an exothermic process. You dissolve. I know we don't have goggles on, but I think we'll be fine. So I'll pass these around and kind of put the things on. And I like it because you can actually tell the granulation. The granulating one is the calcium chloride.
Oh, interesting.
In Chem 1, did you guys do a heat of solution where you dissolve the ammonium chloride?
I remember that in Howard Tree. I remember that.
So that's not a chemical reaction, and in my intro to Gen Chem, a lot of times students will think, they'll try to tell me it's a chemical reaction. It's a physical reaction. All right, Smarty. Okay. Okay. So dissolving table salt, sodium chloride, again, we can think of it as stepwise, where you break the crystal lattice structure. This says that it's going to require energy. Your enthalpy of breaking the stratus, you know what I mean, will be positive. And then we have the hydration of each of the cations. Okay, and these will be, bonds are formed, energy is released. Okay, and you could add them all together, and I don't have the number here, but I looked it up, and I got this table from the internet. So sodium chloride is looking to me like it's endothermic, right? Okay. The heat of solution is what we've been looking at. So if you have a negative heat of solution, that's going to be exothermic. So we don't do much with potassium hydroxide, but a really common base to use in the lab is sodium hydroxide. And I'll tell you, when you dissolve sodium hydroxide, I don't know if it's this exothermic, but sodium hydroxide gets really hot. Okay, and that just means that the energy released when those bonds are formed is greater than the energy required to break the crystal lattice structure. Cool. So these are, as far as I could tell, I didn't chase them down, but these look like, yeah, bonds are being formed. These are just kind of the individual ions when they are hydrated. Okay, this table in and of itself, to me, doesn't help a little lot because we need kind of the corresponding. If you have, for instance, if you had barium hydroxide, well, you could use these two energies, you know, at the end, but you'd need to know how much energy was required to break the crystal lattice structure of the barium hydroxide repeating units. So I suppose. Okay, yep. So I promise we get to it. So these you should be able to do. So let's take a quick look at them. So these will be due on Monday. And then on Monday we'll finish up talking about Le Chatelier's principle, and we'll go on into part 10. Le Chatelier. I've heard that pronounced different ways too, but that's how I pronounce it. Okay, here's what these look like. And they kind of combine a little bit with solution concentration and solubility. So you recognize the table that we looked at, kind of the 6 different salts and their solubility related to temperature. So this first one says use that figure, and you're supposed to knock out what is the molality of ammonium chloride if you're right at saturation. If If you're right at saturation, you're right on the line. So basically what you're going to do is find ammonium chloride, which is the green one, go to 40 degrees, come over here, okay, and that's going to be your grams of ammonium chloride per 100 gram of water, which is your solvent. Then you need to combine that, as the way I think of it, with what we talked about with regard to solution concentration. So remember what molality is moles of ammonium chloride per kilogram of solvent. Okay, so you basically have to knock out the molar mass, I think, of ammonium chloride to get from grams to moles, and then you have to introduce a term to go from grams of H2O in the denominator to kilograms of H2O, and it should be fine. Not too bad. The next one, we're picking on potassium perchlorate down here. And here they say what will be what temperature will, let's see, at what temperature is the right at saturation of 0.200 molal? And to me, what I did is I unpacked 0.200 molal. What does that mean? 0.200 moles of potassium. I think that should be a 4. Perchlorate, yeah, sorry, per 1 kilogram of H2O. That's what it means. And so what you probably figure you're faced against is basically turning molal into grams of KClO3 per 100 gram of solvent.
I'm laughing because on yesterday's homework or whatever, I couldn't figure out where you kept getting 7 grams of whatever. I'm like, where's she getting 7 grams? And it's a question mark.
Oh!
Like, I can't figure that out.
Lots of 7s. Oh, dear. Yep. Now we know. So once you have it in these numbers, then you can actually just go along and find that on this and see what temperature it corresponds to. And last but not least, you get to use that table again. So kind of in the little paragraph building up to the question, they go ahead and describe how they made their solution. Potassium perchlorate, correctly written with the right formula this time. 20 grams of that is dissolved in 50 grams of water, 3 sig figs for both masses. All right. So to me, and I read through A and B, one of the first things I would do is go ahead and basically take that grams of that ratio of solute to solvent and knock out what it really is in grams of KClO4 to 100 grams of H2O. That's what I would do. And then A says, go ahead and, A says, just consider the temperature of 40 degrees. Consider this temperature right here. If you have what you came up with in orange here, if you have that concentration of KClO4 to water, 100 grams of water, are you above the line? Are you below the line? Are you right on the line? Are you undersaturated? Are you supersaturated? Are you right at saturation? It doesn't say are you right at saturation. But B kind of implies you're undersaturated. Okay, because B, the follow-up question says, if you are unsaturated, okay, how much KClO4 do you need to add to get to right to saturation? Okay, so it's kind of a follow-up question. To me, says that A is probably undersaturated. But you need to prove that to yourselves. And I don't have a lot of suggestions for B. I just simply say that at this point, you know, oh, I know. I said I would pick off what is the sweet point, what is the saturation amount, what is on that line right there. I come over here, how many grams of KClO4 do you need per 100 grams of H2O? And then once I had that, I would use what it was to kind of massage how much do I need to add. So that one, I had a hard time giving hints. I would just have to kind of feel my way through the problem. It probably, honestly, I can kind of remember doing this, and it has to do with ratios. I think I end up using ratios, which I say, don't use ratios. But sometimes I'm like, that's what makes sense to me at that point, at the end of the problem. Okay? So, that's it, man.